Hey everybody! I'm trying to come straight on stage, but I keep turning to the right. I keep turning to the right because I'm experiencing the Coriolis Force. If I'm in the northern hemisphere, Coriolis Force will always turn to the right. Hey, welcome to the Epic Flight Academy. This is the Private Pilot Ground School course, and my name is Mike Thompson. Now, to be successful in the course, there are 3 things. Number 1, please be sure to study this material in Epic's online Schoology course. Number 2, you're going to use these videos to parallel the content in that course. And number 3, be sure to review all of this with your flight instructor. Now, what about that Coriolis Force? It keeps turning to the right. Yeah, take a look at this diagram here. Let's imagine we were visiting Santa Claus and we're standing up here at the North Pole, and that year for Christmas, Santa gave me a soccer ball. Now, I'm standing up here at the North Pole and I am going to kick that soccer ball straight south. Now, I've got a pretty good soccer kick, and as you can see in my diagram, I'm kicking it all the way to Brazil.
You what?
Yeah, that's right, all the way to Brazil. If the planet were not rotating, that soccer ball would come straight south from the point I kicked it all the way to Brazil. But in fact, of course, the Earth is rotating, and this brings about the Coriolis Force. Now, it's important to understand which direction the Earth rotates. If you look at the globe here, you can see the North American continent moving toward England or Europe. Okay, that's the direction of the Earth's rotation. Now let's go back to that soccer ball. I'm standing up by Santa Claus's house and I'm going to kick that soccer ball to Brazil. Now the soccer ball is still going straight south, but because the Earth is rotating underneath of it, look where it lands. That soccer ball actually lands out near Equator. So the Coriolis Force turns it to the right. The soccer ball is going straight, but its path is curved to the right because of rotation. Now, let's imagine if we were in the South Pole and we're standing out there amongst the penguins and we're going to kick this soccer ball straight north. Because of the Earth's rotation, Coriolis would turn it to the left. But let's not confuse ourselves, since at least initially we're going to do most, if not all, of our flying in the northern hemisphere. We'll just stay focused on the fact that Coriolis turns to the right. Now that is the Coriolis effect, talking about air moving toward the equator. Now, the Coriolis effect also affects air moving along the equator. The atmosphere is pulled along by the Earth and appears to turn right as we move north, because as the atmosphere is being pulled along parallel to the equator, as we move north, we're covering less and less ground. You can see an example of that here in this diagram. Now, also in this diagram, you can see that that effect becomes stronger the closer we get to the poles. Why? Because there is less and less surface area to cover as we move closer and closer to the poles. That's called the conservation of angular momentum. And I know that sounds like a big concept, but it's really just the same as this dancer. And I think many of us have experienced this. As we're spinning around in a circle, when the dancer puts her arms out, she tends to move slower. That would be the atmosphere closer to the equator. As the dancer pulls her arms in, she spins faster. That would be the atmosphere as it is drifting north toward the pole, and that Coriolis effect turns it to the right more and more the closer we get to the poles. So far we've talked about the Coriolis effect and its effect on the horizontal movement of air. Now, secondly, when it comes to global circulation, it's just as important to understand the vertical movement of air. Now, in order to understand that, let's begin with this diagram where we look at how the sun heats the Earth's surface. Notice in the diagram, I want you to I want to call your attention to two key things. Number one, the sun's rays are hitting the Earth's surface at a different angle. You can see closer to the equator, the sun is more direct, and as we move towards the pole, that same amount of incoming sunlight is spread over a larger and larger surface area. So, of course, the planet gets cooler near the poles. Now, the second thing to notice is that the sun will heat the Earth differently depending upon the surface. Land masses will heat and cool faster. Water, such as the oceans, will heat and cool slower. This will affect the vertical movement of air. Now, we know that sinking air is cooler, it's less moist and more dense. Warm air is more moist and tends to rise. Well, do you ever wonder exactly why that happens? I want you to take a look at this diagram and see in both cases, the blue column and the orange or red colored column, we have theoretically the same volume of air. But notice, because the blue column is cooler, more of that air is settling to the bottom. Notice we've outlined here the halfway point in these two vertical columns. So if you can imagine they have the same volume, you see how in the red column it's more spread out, and in the blue column it's more condensed near the bottom. And this is what we mean by cold air sinking and warm air rising. That warm air rising we know as convection. The final part of the vertical movement of air that we need to understand is convergence. Now, remember, we just talked about convection. This is convergence, and you can see in these pictures an excellent example of convergence just happens to be Florida itself. As air is moving in from the Atlantic and in from the Gulf of Mexico, this air converges, bumps into each other, and rises. Vertical movement of air. So, thus far, we have talked about the horizontal movement of air and the vertical movement of air. Now, one more key thing to understand before we discuss atmospheric circulation, and then it's all going to come together and click. And this third and final key is called PGF, or pressure gradient force. Now, what does that mean? Remember, atmosphere will seek a balance. So it will flow from a high pressure and into a low pressure. If you take a look at our diagram here, you can see that the red line is the pressure gradient force, and it turns right in both cases. In the high pressure, it's flowing away toward low pressure, and you can see the red line, which is our pressure gradient force, being turned to the right by Coriolis force. Now, in the low pressure, it's the same thing. The red line is the pressure gradient force flowing into or toward the low, and again, it is being turned to the right by pressure gradient force. So if we can put all three of these keys together, horizontal movement of air, vertical movement of air, and pressure gradient, we are about to master an understanding of global circulation. In global circulation, there are three major cells: the Hadley cell, the Ferrel cell, and the polar cell. So let's start here with this diagram. We can see that the Earth is much warmer near the equator. And again, we know why. And you can see this air starts to rise, and at some point it will start to diverge both north and south. Now, at what point will it stop rising? That, my friends, is the tropopause, or the bottom of the stratosphere. The air will then proceed to the north, proceed to the south, and as it travels toward the pole, it starts to cool and will fall towards the surface of the Earth at approximately 30 degrees of latitude. Now, in this diagram, we are disregarding the Coriolis force. Now, when we add Coriolis force, both north and south and along the equator, we can see in this diagram, Coriolis force is turning the surface flow to the right, and that was the Coriolis coming from the pole toward the equator. We also see Coriolis turning the aloft flow to the right, and that was that horizontal or flow parallel to the equator that we talked about with Coriolis force. Now, that circulation creates what is called the Hadley Cell. At the equator, the air warms. As it rises, it starts to cool, losing moisture, is deflected to the right, heading north aloft. It's moving over a smaller distance. It creates high pressure when it starts to sink near 30 degrees of latitude. And again, Coriolis force directs it to the right at the surface, and these are called the trade winds. As it flows north and cools and dries and drops down at 30 degrees of latitude, it creates these high pressure areas. Now, let's jump from the Hadley Cell all the way up to Santa Claus's house, and let's go to the North Pole. The polar cold air sinks. Now remember back to our two vertical columns of air, red and blue, and we looked at why that cold air sinks and is more dense. As this cold air sinks and it starts to flow south, it is also warmed by compression. And as it flows south, it starts to warm, and at approximately 60 degrees, it is ready to rise back up, creating predominant low pressure along 60 degrees of latitude. As it flows south from the pole, it is turned right in the northern hemisphere, and the wind appears to come from the east. These are polar easterlies. If it's flowing north from the south pole, Coriolis force turns it to the left. Again, it appears to come from the east. So at the south pole, we also have what we call polar easterlies. Now, in our next diagram, we start to see the whole picture. And I want you to notice something interesting. While air is sinking at about 30 degrees of latitude, and it's rising at about 60 degrees of latitude. This is causing low pressure at 60 degrees of latitude, higher pressure at 30 degrees of latitude. Now, remember the pressure gradient force? The air will flow from high towards low, or in this case, from 30 degrees of latitude toward 60 degrees to fill in that low pressure. This results in what we call the Ferrel Cell, and you can see that here. The Ferrel Cell is caused by the other two cells. Air coming south from the pole, warming and rising at 60. Air is drawn north from the high pressure at 30 degrees toward this low pressure at 60 degrees, where it rises and returns south aloft. This creates that Ferrel Cell. Now, at 60 degrees, these two airflows, the polar cell coming south and the Ferrel Cell coming north, are converging. Remember convergence? These two airflows collide at 60, converge, and start to rise. And the warmer air coming from the south rides up over the top of this air that it's converging with at 60 degrees. This creates the polar front, and that air continues north, getting colder and drier, and it sinks at the poles. So now you can see how this diagram puts together the whole picture of all three cells. You can also see how the three basics of the vertical movement of air that we discussed, the horizontal movement of air that we discussed, and pressure gradient force are critical to understanding this global airflow and circulation. Well, folks, that just about wraps it up for today. Join us next time.